Will. Bon. Allô, Solo, donne-moi. Hello.
Ya, sorry Dario, ya mo ton zut no mal mo wa zut tu. Ton mo zut? You.
Solo.
Ton mo?
Yeah, okay, good.
Unisi pan mo jitu.
No.
Man.
Donne-moi bien, moi.
Ya, tu di no man mo wa screen tu. So pita.
Allez, mets ça.
Ya, ali, mo mute mo.
Yeah. Thank you everyone for attending. So the topic today was a little bit mislabeled in the advert, and so the object of this talk will be the blue economy in Seychelles, and principally an example of the Seagrass mapping and carbon assessment project, which was conducted which has been conducted since 2019, and its goal was to preserve 100%, how it leads to the preservation of 100% of the blue carbon habitats in 2030. So the Seychelles has been recognized worldwide for its approach on blue economy, which is an approach to marine conservation. And the definition that was proposed by the World Bank for the blue economy being the sustainable use of ocean resources for economic growth, improved livelihood and jobs, also opens to the health of ecosystems, of ocean ecosystems. And this is what this kind of project is about, mostly the health of the ocean's ecosystems. And so all the philosophy and the willingness of the country to define its blue economy is contained in one document that is called the Blue Economy Roadmap that was published in 2018, and where all the different sectors are described and all the actions toward blue economy are clearly defined, including one of the main aspects of blue economy, which relies on the distribution of space for the different activities that are organized. And this is the object of the Marine Spatial Planning of Seychelles. It was an initiative that started in 2014. And within this initiative, some consultations with different stakeholders have been organized to define 3 different zones and to achieve the first milestone, or actually it's their 3rd milestones, but it's one of the main milestones in the terms of conservation, which is the protection of 30% of the habitats, of the marine habitats within the EEZ of Seychelles. So the EEZ of Seychelles is 1.36 million square kilometers. And this Marine Spatial Plan has defined 3 different zones. Zoning 1 in its zoning exercise. So the zone 1 is the high biodiversity protection areas, which means that there's a lot of restrictions applied to any economic activities taking place. Zone 2 is the medium biodiversity protection and sustainable use areas, which is part of the 15%, so the second half of this milestone. And the zone 3 is the multiple use area, which is basically not restricting any activities, but some of the activities may rely on permissions, on permit, on licensing. Okay, so this is how the spatial planning has been organized. So in green, in dark green, here, for example, you've got the zone 1, where most of the restrictions apply. And the light green is the zone 2, and the rest, including the region around the granitic island, is in zone 3. Okay? So on top of this zoning, we've got several layers that have been produced during this Marine Spatial Planning exercise, which is called the MSP Atlas, and the MSP Atlas is accessible on their website. And you can see here a description of a few of the maps that are available. So apparently there are about 300 layers of data that have been compiled. And among those maps, I extracted one of the most interesting maps for us, which is called the Seagrass layer, that describes the regions on the Mayo Plateau, in the Amirals Banks, and below in the outer islands, that describes the distribution of seagrass depending on different levels of soil occupation, which is the low in yellow, light brown is medium, and dark brown is high. So when we look at that, we see that most of the areas that are located on the Mayo Plateau are occupied by seagrass, and some in the outer islands also have, especially the atolls and inside the atolls and some of the banks, they are also occupied by seagrass from medium to high, which is a good news. So during this exercise, we looked at the different surfaces that were occupied. We extracted the data, and we looked at how much seagrass do we have in Seychelles, and the numbers were striking because it ranged from 16,000 hectares to above 2 million hectares, depending on the source. So the Outer Island project only focused on the Outer Island, which may explain why it's a bit low. But the Allen Coral Atlas that focuses on the reef occupation found about 26,000 hectares. And when we compared that to the SMSP Atlas and this seagrass layer, we were shocked to see that it was about 2 million hectares, above 2 million hectares. But we found out that this data was based mostly on remote sensing. And when we compare this projection for the EZ of Seychelles to the numbers that are obtained worldwide, then it makes it a little bit more clear that there's a lot of discrepancies between the sources. For example, here, the publication by Frederick Shaw in 2003 gave about 177,000 square kilometers. We are speaking of a worldwide distribution, which explains why the unit is not the same. And his revision in 2018 gave about the double of this value, which is about the same order of magnitude of Claude Charpie-Roubaud and her publication in 1990. But when we compare with the publication by Jean-Pierre Gattuso in 2006, with above 4 million square kilometers, we see that the same kind of scaling applies between the local space or the national space and the mondial space. So we needed to find out exactly what it was about. Is it more 2 million hectares or more 26,000 hectares for Seychelles? And the reason, most of the reason why we get interested by the seagrass is because seagrass coexists mostly between the coral reef and the mangrove in a continuum like we have in Seychelles. So we've got, so the continuum is the different habitats that we cross from land to the ocean. And the mangrove is the most terrestrial one. Then we've got the seagrass, which is called the subtidal habitats, like the corals, because they are below the surface of the ocean. So the reason why we are interested by the seagrass is because they are pluriannual plants, so they grow from a vegetative stage, mostly in Seychelles. They produce some flowers eventually, and they stay there for a few years, actually a few hundreds of years, as we've discovered. So they provide different services, which are called the ecosystem services. They consist of an habitat for different species, and also refuge for the larvae or the juvenile stages of some fish. Because they are slowing down the currents at the bottom, they improve the water quality by reducing the amount of particles in suspension, reducing the turbulence. And then because they accrete sediments in the near shore, they act as a coastal protection. And in some regions, they also have cultural or societal benefits. And one example of the societal benefits is during the southeast monsoon season, for example, when the fishermen cannot safely go deploying their traps or lines in the open ocean, they shelter in the lagoon and they deploy their fish trap, which helps them gain a revenue for their families and also feed the community. And finally, they play a role in climate because their behavior of sequestering sediment, accreting sediments and burying sediments contribute to what we call carbon sequestration. So for those two reasons, coastal protection and climate action, they are ranked as a nature-based solution for adaptation because of the sedimentation and for the mitigation of climate change because of carbon sequestration. Their distribution is worldwide. We've got temperate seagrasses that stem from the Arctic region and mostly in the Baltic Seas, but all the coastlines, the seagrasses in green here. So most of the coastline that are shallow enough have seagrass, and we are interested in the tropical seagrass The tropical seagrass are different, so they occupy the same habitat, but they mostly, it's different set of species. There's almost no overlap between the temperate species and the tropical species. So in total, we've got about 72 species, and in the tropical seagrass, we've got about 48 species. And in Seychelles, we've discovered that we've got more or less 12 species, more or less, because some of the individuals that we found are still under the scrutiny of the experts to define the species level, or if it's a family or if it's a species. In terms of carbon sequestration, those habitats, mangrove and seagrass, as we have here in Seychelles, they are much more efficient at sequestering carbon than any other terrestrial habitat. So here, for example, we've got the carbon storage capacity of seagrass meadows and mangroves, and the dark blue only accounts for what is incorporated in the soil beneath those ecosystems. And if we compare the performance of a mangrove or a seagrass meadow with a boreal or a tropical forest, we see that we are about 30 times higher in terms of carbon sequestration. And the same applies for the burial rate, which is the capacity to store the carbon in the soil, and the burial rate are about 75 times higher than in the dry soil. Okay? So those ecosystems are growing in wet soils, so the moisture in the soil, the water contained in the soil, switches the ecosystem, the bacterial ecosystem and the degradation to other types of reactions that improve the sequestration of carbon, that reduces the amount of recycling of this organic carbon and its return to the atmosphere. This is what is exactly the advantage of having seagrass. How it works, it's very easy. So you've got the plant, which is a photosynthetic organism. This photosynthetic organism uses the carbon dioxide that is present in the atmosphere and that dissolves in the ocean by chemical processes. This carbon dioxide is metabolized into organic matter, and this organic matter is in the form of carbohydrates, penetrates into the plants and is stored in the root system, in the rhizomes here. And as the soil, as the sand is added to the soil, because the canopy creates a reduction of turbulence, then the sand accumulates, and then the plants follow the accretion, and the root system continues to store and eventually detaches, and new shoots appear on the top, so which creates a burial of the organic matter that is contained in the soil. Other source of organic matter is the grazing by different organisms when they live in the seagrass area. They graze the plants and they release carbon that is also incorporated in the sediment. And as this happens, then more organic matter is accreted, and then the soil level increases and leaves behind some of the metabolites and products that are called refractory carbon. And that's an ultimate stage. So you see here all what is there and there. So the epiphytes, all what has been gained and what has been left behind constitutes what we call the total stock of carbon. And this can range from a few centimeters in the sediment to a few meters in the case of, for example, mangroves. Here, we focused our study, we standardized the measurement on the top first meters. Okay, so this carbon sequestration has an economic value. If you look at all the ecosystem services that are provided by the seagrass, we see that this carbon storage has a value of about $400 per hectare and per year. So if you multiply this number by the amount of seagrass that we have in Seychelles, we can calculate the value of this ecosystem based on the seagrass. And the seagrass is also exposed to different threats, coastal development, creation of harbors, sand extraction, the activities that deploy anchors and buoys from the seafloor create some scars that are difficult that depletes the soil from the seagrass, and also in regions like here in the Everglades National Park, you see that the activity of boat creates some scars on the seagrass coverage. It's not the only threat, but that's the most direct threat. And in the Indo-Pacific region, since 1945, the first assessment, we noticed about 16% loss. And this 16% loss is only half of the value of all at the global scale, because at the global scale, mostly in temperate regions, we've got about 1/3 of the seagrass that have already disappeared. So there's a lot of concern about their conservation, how we can action plans to make them protected at the national level. And the way that we've scaled that was by using the Paris Agreement. So the Paris Agreement is one of the agreements that the country signed in 2015 in the wake of the COP15 in Paris. And during this Paris Agreement, it was agreed that all the countries would make effort to reduce their carbon emission to try to lower the increase of global temperature to 1.5%, which was the target at that time. We know that now we've passed that even 5 or 6 years before the deadline that was put in this Paris Agreement. But still, we need to continue to try to improve the carbon sequestration. And one of the commitments that was made by Seychelles, so the INDC stands for the Intended Nationally Determined Contribution, which is one of the demonstrations of the willingness of a country to act under the Paris Agreement, was to promote the ecosystem-based adaptation and mitigation by the way of protecting coastal ecosystems. Then, to write its fully potent nationally determined contribution in 2021, the government of Seychelles asked the World Bank a report that to which we contributed in BERI. And in this World Bank report, we tried to mainstream the blue economy in Seychelles, and we articulated this report towards the conservation of coastal ecosystems to end up with the nationally determined contributions published in 2021, where the government of Seychelles clearly stated that both mangrove and seagrass are relevant for climate resilience. So that was a first step. And then the second step was that Seychelles committed to protect at least 50% of its seagrass and mangrove ecosystems by 2025, and 100% in 2030. So since that was published, then there was a need to clearly say where were the seagrass and how much did we have to cover, okay, in terms of protection. Then in 2018, there was another agreement that was signed by Seychelles, which was called the Perth Recommendations on Blue Carbon Management. That was a document published by the Indian Ocean Rim Association, that where all the countries in the Indo-Pacific regions, or mostly, yeah, so from South Africa down to Australia, recognize the need of blue carbon ecosystems, so salt marshes, mangrove and seagrass for every country, for the benefit of the country. and their ecosystem services. They recognize the need to take action now, to share knowledge and data, and to create international partnership. Okay, not to do that in silo, country by country, but to share resources and methods. And so Seychelles was not the only one to sign. Australia, Bangladesh, Comoros, India, Indonesia, Iran, Kenya, all those different countries adopted these recommendations to improve the research on blue carbon and the determination of the carbon habitats, the blue carbon. So how do we align with our nationally determined contributions? So the publication of the NDC was supposed to be in 2020 according to the agenda. It was pushed to 2021 because of the COVID-19. And last year we completed this project, and we did what we call the first global stock take of the seagrass, determining the amount of seagrass that we had, but also addressing the amount of carbon that they store. Okay? The second NDC, full NDC, is expected in 2025. Hopefully it's going to happen. We will see, maybe 2026, depending on the progress. And then in 2028, we've got the second stock take that should take place to see if there's any difference, gain or loss. Okay? Hopefully gain if the production is achieved by 2025. And 2030 is the first our milestone of 100 production, and to tend in 2050 towards the carbon neutrality, to try to flatten our emissions and of CO2 to the atmosphere. So to do that, two different projects were organized. One concerned the mangrove, that was called the Mangrove Blue Carbon Project, that was implemented under the Swire Fish and Jeff. It was organized, the activities were organized by the Deakin University in Australia and the Ministry of Environment, and this project addressed the mapping, the carbon in the plants, the carbon in the soils, and the modeling. Some of the mapping was not complete. And in the wake of this project, the team published what is called the Seychelles Blue Carbon Roadmap, which is a document that expressed the ambitions of Seychelles to develop its research towards blue carbon, and gives guidelines on how to reach the good practices. And the second project was the one in which the University of Seychelles was involved, which is called the Seychelles Seagrass Mapping and Carbon Assessment Project, where we did a complete mapping of the seagrass in the region, in EZ. Okay, first time in the world that a global mapping is undertaken. We assessed the carbon in the plants, the carbon in the soil, and we did a modeling approach to this. So, of course, this was not only us. So, the Future Renewable Trust was the funder of this project. We worked closely with the University of Oxford, who helped us to undertake all these activities. William Rollins was the main researcher. The German Aerospatial Agency helped us with the processing of the satellite imagery. The CCAT was the main holder of the budget of the wetland project, which incorporated this project as well. And we relied a lot on many different NGOs, but one of the most important one was the Island Conservation Society, who deployed all our methods in the outer islands, because we focused on the main granitic islands, and ICS was responsible for doing exactly the same in the different islands where they had access. So this project was structured in different parts. So the first part was the remote sensing. So the remote sensing to create an imagery, to stick together all the satellite images, to make a massive mosaic of the region, and to look at algorithm that would allow us to detect the presence of seagrass from the satellite imagery. The second aspect was more the field work undertaken under this project that consisted in taking pictures of the sea floor and also at taking sediment cores to detect or to quantify the amount of carbon that was stored beneath the sediment. And the last aspect was to treat the data, to compare the data with other regional and global data to see if we are coherent, and then to release this data to the government, because at the end of the day, it's going to be the property of the government. We can do the promotion, but most of the data will be incorporated into different databases, GIS databases for the distribution, and also carbon database, because the ambition of the Paris Agreement was to incorporate the sequestration of the seagrass into the national greenhouse gases budget, which is one of the documents that accompany the nationally determined contributions. So looking at the seagrass is a technological challenge. Okay? Seagrass are underwater, so they can be just beneath the surface, sometimes exposed when it's very low tide, so below around 0, down to 35 meters depth. And in the Saya de Malabank, we also went down to 75 meters where we found seagrass. So imagine when you look at your feet in the water, sometimes it's not very clear, but now we have to detect these plants from a satellite that is 300 kilometers above our head, and to try to see if the seafloor is covered or not by seagrass. So this is extremely complicated, and this is an example of this is a map. So this is one of the small tiles of the mosaic that we got, and all the black here, or dark, constitutes mostly, obviously, seagrass. So we are interested in this point, and we need to confirm that this point is truly seagrass. Okay. So this is all the complexity of the satellite data. Here I represented different resolutions. So all these are different types of visualization tools. Landsat is one of the satellites that looks at the land, okay? And you see that Landsat has a resolution on the floor of 30 meters, squares of 30 meters by 30 meters. And you see that mostly what we see is big pixels, okay? If you compare here with the finest image that we can get, which has a resolution on the floor of 4 centimeters, so something that looks like this, and you see it's exactly the same region that is mapped with all those different sources, and we see that with the drone we can clearly see all the different regions, and we can clearly draw some lines around the seagrass that is present. The problem is that we cannot take drone image of the entire EZ. Okay, it's impossible. It would take ages to do that. Even if we multiply the number of drones, it's not achievable. So we need to find the good compromise between the worst case scenario of the Landsat and the best case scenario of the drone. And we selected 2 different sources. One is Sentinel-2. The advantage of Sentinel-2 is that It's a European satellite that passes over Seychelles several times a week. So we can get reliable data, but the resolution is 10 meters on the floor. Okay? We need to buy the images because it's not for free. Okay? It's for free upon agreement, but there was no agreement at that time, so we needed to look at ways of gaining those images, because not all the time these images are kept. Okay? When the satellite passes over water, it consumes a lot of data, and most of the time they erase the images. And if you've got a tiny atoll in the middle of a big ocean, then most of the time it's not retained. So we need to tell ESA, which is the European Spatial Agency, to keep those images for Seychelles, which is the reason why they are not fully accessible. And then we use another type of satellite imagery, which is a bit finer, 3 meters on the floor, which is called PlanetScope, which is for free. But the main difference between the two is the type of data that we obtain. So Sentinel is what is called a multispectral bands satellite, which looks at the visible range, but a little bit beside the visible range in the infrared and ultraviolet bands. So we've got about 7 bands that can be analyzed withdraw an algorithm to detect the seagrass, when PlanetScope were just RGB images, the same as the JPEG image that you take with your smartphone. So 2 different types of analysis had to be conducted based on the availability of those 2 different sources. And so this is the object of what we call the ground truthing exercise, which was to take 1 pixel on the satellite and to compare this pixel with a photo quadrat, which is a picture that we take at 1 meter above the seafloor. Okay? To do that, we needed to cover as much area as possible in the ocean, in the different regions, to look at different points in this quadrant, to fill up the gaps here, and to create an algorithm that would compare these points with images like this, to try to make a rule of presence or absence and distribution. So here we've got an order of scales from the shoots, which is that, okay, to patches, which are basically a little bit bigger than that. We've got a few patches here, and to the ecosystem that has a scale of a few hundred kilometers. So from the north to the south, we've got about 1,000 kilometers in Seychelles. So we needed to upscale the smallest images that we get to get the idea of the amount of seagrass in the entire region. So to do that, we build a model based on so this is the EZ. So we distributed the EZ in 3 zones, depending on the amount of cloud coverage and the treatment of the images. So we have the north, which consisted mostly of the Malay Plateau and some regions on the Malay Plateau. Then we had the central, which is the Amirans, Lat-Kuwaiti, and the Alphonse group, and then the south region, which is mostly the Adabra, with Adabra and Cosuelo, and the Farpar group. And those 3 different regions constituted most of the set of data. So what we did with that, so we had an image data set that we built over about 6-7 years. So to make sure that 1 pixel was really reflective of what was on the ground. Okay? So we constituted stacks of images, of satellite images, to detect the presence of seagrass. And we used the 2 different sources, Sentinel-2 and Sci-Fi, the other one, PlanetScope data. And specifically for Sci-Fi, from 9 1995, we made a publication because this is kind of an exotic data set for aquatic imagery. Generally, PlanetScope is used for terrestrial imagery and had never been applied to aquatic imagery. And it was one of the main technological progress that we made to try to incorporate this into aquatic imagery. Then with this multi-temporal composition, so for 1 pixel we had about up to 6 layers to describe this pixel. Some had cloud coverage, so needed to be removed, but for each pixel in the EZ, we made this imagery. Then we removed all the regions that we were not interested in by removing the lands, removing what was very deep and was likely not hosting any seagrass. And then we used machine learning to train the algorithm to detect the seagrass based on some ground truth images that we provided. So, Stuart, did you come with us? No? And about 75 people in Seychelles contributed to the effort of ground truthing those seagrass, which means that we all went snorkeling and diving with small cameras to take images with the GPS on our heads. And then 80% of this data set was used to train the algorithm, so it came with suggestion and we had to validate or to refute the suggestion. And then the 20% remaining was used to classify the region, which means that from transects that were made like this with images, then we could describe the entire region using the satellite image. Okay? So what is here in yellow corresponds to regions. So this is the Basin d'Antralin, for example. And this region is where the seagrass are verified by ground truth. Okay? So to give you an idea of the research effort of this project, so for coring we took about 90 cores, that needed to be analyzed. 50 vegetation and root samples that were analyzed for carbon. A little bit less than 1,000 drop cams, which is a camera that we deploy from the boat when the conditions are not good enough or when it's too deep for divers to take photoquadrats. And we took about 41,000 photoquadrat images to train this algorithm and to detect the seagrass. So, of course, this could not be hosted on computer. So we used the algorithm that were provided by the Google Science Engine to host all those data and to process all those data. And this represents about 270 terabytes of data to be analyzed and treated. Okay? So this is a few pictures describing the different activities. So it could be underwater detection. So the guy here is holding a camera. Then he has a line that connects to a globe like this, on which there's a GPS. So which means that we join the GPS track with the image dates and time, so that we know which is the position of the image that was taken. The problem is underwater you cannot use a GPS, so you're obliged to have this system that is pretty efficient. And sometimes, so you see here, we needed to have fixed quadrats, because this is what the image gives. So we calibrated the distance from the lens of the camera to the soil to have always the same surface covered by the camera. Okay? So in the absence of a laser tell us the distance and to calibrate the pixel on the camera. We needed, so we used a plumb line, and then we put the plumb on the floor, we take a picture. We move by 5 meters, we do the same. So this was about what was done. So sometimes it was made by scuba, sometimes it was made just by snorkeling. And this was about 437 days of data collection in total. And this is what we end up with. So this is an example of the Sainte-Anne Marine Park. So you recognize Hawai'i, Long, Little Cerf, and Sainte-Anne Island here. And all the regions colored in yellow corresponds to seagrass meadows in this region. Okay? And we did the same for all the Mahé Plateau. Okay? Here is a focus on Mahé, and you see here, this is Anse-au-Pin. Here you've got Anse-la-Mouche and the Lazare. Here you've got Anse-Royal with a bit of seagrass. And here you recognize the marine parks here of Béternay, where there's a huge meadow. Okay, so, and here is the image that I presented before with Sainte-Anne. Same for Liege, same for Pralin, and so we covered all those regions. So this is an example of the Rush. For those who have been to the Rush, you may have noticed that it's fully covered by seagrass, and that's good news. This is the Admiral's Banks, and here an example of the Alphonse group. So we covered about 16 of the outer islands, plus the Mahé Plateau. Some regions of the Mahé Plateau, because our study was restricted because of the technical constraints of deploying staff very far, was constrained to the inner island regions. So Mahé, Pralin, we didn't go to Silhouette to do this. And in April this year, the Greenpeace came to us and offered to refine the data into this region, which has been a game changer for us, because since we understood a little bit better how the seagrass was distributed here together with coral, then we could extrapolate to the entire rim of the Mahé Plateau, and we increased the coverage by 14,000 hectares. Okay. So in total, sorry. Here, so in total, the coverage of seagrass in Seychelles is about 160,000 hectares of seagrass, a little bit less. But it's in the range of 16,000 hectares in Seychelles. So most of the distribution is on the rim of the Mahé Plateau, not inside the Mahé Plateau, as it was stated before, and in the Admiral's Banks. So this represents about more than half of the seagrass in total in the region. Okay. And another exercise that we did with this project was to look at the different species, to make a species inventory, because it's important in terms of conservation to know what to conserve, which species are present. And so we've got here the 12 species with their absence or presence. Sometimes some are dominant in some regions, some are not dominant, some are multi-specific. We call that multi-specific assemblages. And what you see here, but I will come back on this part of the project, is the Creole names that were assigned to different groups of those seagrasses. So the reason why we gave them a Creole name was to make them more accepted by the population, because you can only protect what you like, and what you like is what you know generally. So this was, but I will come back at the end and show you some examples. So what we've discovered mostly is that we've got two different types of seagrass assemblages. We've got a lot of seagrass present in the outer island that consists only of a few species, mostly dominated by thalassodendron, which is this one that looks like hands, the fan, okay, Seagrass and Thalassia, which is the one that is praised by the turtles, okay? And when we move on to the main plateau, that's where we've got also those ones, but mostly all the other species. So the tiny islands here compared to this big space contains most of the biodiversity of seagrass, including what we call the grand feuille, Enalus acoroides, which is a very rare species and that is very impacted by anthropogenic activities, the construction of islands, the reshaping of the coastline, and tends to disappear right now, but it's one of our champions of carbon sequestration as well. Okay? And if we now look at the distribution, the overall distribution of these seagrass into the zonation of the Marine Special Plan, we find that in Zone 1, fully protected, we only have 7% of the seagrass now in 2024, since we need to protect them, half of them by 2025. So it's going to be challenging because we need to work on the 93% that remain to try to find a way to prevent the exploitation of the sea bottom and the impact on the seagrass. Okay? So if we look at the distribution of those seagrass, you see that, so this is the outer islands, including the Nile Plateau, and this is the granitic islands. So the granitic islands almost have no seagrass protected except the national parks. Okay? So because the granitic islands are basically in Zone 3, the only regions where seagrass is protected is when they become part of the national parks or the shell reserves, like in Ansopin. And even in Ansopin, it's even not easy to protect them because there are land occupation and construction projects that they need. Okay? So this is on the outer islands we've got most of the seagrass present. Okay, yeah, okay, 93% that needs to be protected in 2 years, basically. So the second part of this project, so this was the mappings. Now we've got the assessment of carbon. Okay, so how do we do that? Basically, we take the regions where they are, we take cores, and we multiply the amount that we find in the cores by the area to find the surface. So it's a very easy equation, not that easy to do, but this occupied us for about 5 to 6 months, mostly in the lab. So here you see my colleagues taking a sediment core. So a sediment core is a tube. So the tube is 1.2 meters that we push into the sediment, that we take out of the sediment, that we clamp. And so it can be done by foot, or it can be done by scuba when it's a bit deeper. And then we come back, not necessarily to the lab, but to a campaign lab or field lab that we create. And then we start slicing those cores every centimeter to get the samples. And so you see here, this is a snapshot of the core. So we've got the sediment here, we've got the water above. So we take measurements to see how much sediment we have compared to the total to account for the compression. And then we start slicing. So we cut slices, we put in bags. When the bags come back to the lab, then we weight them, we sieve them, and then we compress them in the oven. So this occupied us for about 6 months. mostly 7 days a week. So I was taking the weekends, the students were taking the week, and we were running the average.
Écoutez, ou bien manquer fort.
Unit that we need. And so this is the regression that we found in black, okay? And this is the regression that was found in the literature, which agrees pretty well. We were very satisfied with this type of regression because we tick two boxes. First, we've got a regression that is regional for our use. So this ranks us into a higher reliability level in terms of scientific determination. And the second box is that we can apply that from now on to any of the other samples that we get. So we don't need necessarily to redo this kind of experiment. So this relationship is for the specific assemblage that we have here. Okay? So we did that in the sediment, but we also did that for the vegetation to convert the ash-free dry waste, so the loss of diminution process, what comes out of the oven, and convert that into carbon. Okay? So we've got the carbon in the soil, and we've got the carbon in the sediment, in the plants. And then we compile this into per region, so Cosmedo, Astor, Farquhar, Sainte-Anne, Alphonse, Desroches, Aldabra, Garros, Halin. So we put that all together, so every dot here corresponds to regions that have been sampled for carbon. And so this shows us that even within one site, when we took different samples, we've got a huge variability. Okay? So we need to rely on statistical descriptions rather than on point measurements for the carbon in these regions. Okay, so this shows the high variability and the need to consider to be very careful with the data that we get in terms of the interpretation. Okay. So in total, we compiled all the different sites. We made our math right, and we obtained about 118 tons of organic carbon per hectare. Okay, if you multiply by the 160,000 hectares, and you've got the total amount of carbon, of organic carbon that is stored nationally by the seagrass. And when we compare the performance of our seagrass with the global, we see that we are a little bit lower than the global, but the global is biased by some research that are done in the Mediterranean Sea, where a lot of this science was done and where they have the best performer in carbon sequestration, which is called Posidonia oceanica, which is not our case. Our case, we've got Enalus, but pretty few of those Enalus. But if we compare to the data that is available in the Western Indian Ocean region, we see that we are pretty close, okay, almost the same. So we are not so different from Tanzania, from Kenya, where some of those studies were also done, okay? So this is per hectare, okay? 100 meters or 100 meters. And in terms of estimate, we provided 3 different estimates. We provided the mean estimate, which is the average in each region combined, so the northern part, the central part, and the southern part combined together. But we also provide a high estimate, and we provide a low estimate also to be cautious. Okay? So this is to bracket all those regions. Then another part of the project was also to determine the accumulation rate. Okay, so how to do this accumulation rate? We used the isotope 210 of the lead to calculate the age of the sample in the core. So the core that was sliced in different regions. We analyzed the age of different samples in one core, and we determine the sedimentation rate, the time, the amount of sediment that accumulates in this core, and then knowing the profile of the distribution of organic carbon in this core, we calculated the carbon accumulation rate, which is the amount of carbon that is sequestered per hectare and per year. Okay? So this is expressed in tons of carbon per hectare and per year, which means that, for example, on the Mai Plateau, so this is the marine part, we've got about 2 tons and a half of organic carbon that accumulates every year on 1 hectare. Okay? So we've got very high values like this. We've got a little bit more moderate values in other regions, like in Costa Rica, for example, which is very granity. There's no granite, it's just coralline sand. So the quality of the sand also influences and the proximity to land also influences the sequestration or the accumulation rate. So we made the average, but we decided to use another value, which is the median value. So the median value is the point where you've got half of the distribution before and half of the distribution after. So this gives us more confidence in an absence of bias given by a distribution that would be dichotomic or skewed to one side. Okay, so this was 0.87 is the amount of sequestration, of accumulation that we decided to use in terms of accumulation. So now the budget. If we look at this project, we found about 160,000 hectares of seagrass for Seychelles, compared to 2,195 hectares of mangrove. So seagrass represents about 98% of the surface of blue carbon ecosystems, and the mangrove only 2%. Okay? Although the mangrove is very good at sequestering carbon per hectare, then when you multiply those numbers, you get a higher sequestration in total, because just seagrass is the dominant species of blue carbon in the carbon range here in Seychelles. And in total, we've got a sequestration of carbon that amounts to 524 kilotons of CO2 equivalent per year. Okay, I specifically use this unit because this is the unit that is also used in the greenhouse gas budget, okay, from Seychelles, so that we can compare directly what is sequestered by our blue carbon ecosystems to what is emitted by our human activities. Okay, and so we see that again the seagrass represents about 97% of the total amount of CO2 that is sequestered naturally by ecosystems, provided that they are protected. Okay. So yeah, that was what I said before. So in terms of inclusion of these potential carbon sequestration into the national greenhouse gas inventory, so these numbers represent the amount of CO2 that is emitted per year in 2018, okay, for the year 2018. Also kiloton of carbon equivalent, of CO2 equivalent, and this is extracted from the third national communication that was published earlier this year for the year 2023. So the energy sector produces 518 kilotons of CO2 equivalent in 2018. And this is our 524 for the seagrass, okay, that I put as a negative value because this is what is sequestered compared to what the energy sector is emitting. This is what is emitted by the refrigeration and air conditioning sector. This is what transport is emitting when we drive back and forth to Victoria to drop the kids. And this is what, in terms of CO2 equivalent, what is emitted by the waste in 2018. Okay? And we see that the seagrass, what the seagrass, or the blue carbon ecosystem in general, this is the seagrass plus the mangrove, is commensurate with the amount that is produced by the energy sector. So we can almost offset the energy sector of Seychelles by protecting the seagrass and including the blue carbon ecosystems into the greenhouse inventory. And the second column represents the projection for the year 2030. So when we hope that 100% of those ecosystems are protected, that's the reason why I included this number here. And you see that we do have a large proportion of the total amount of CO2 emissions because of development, because of population also increase. But if we remove this 524 for the nature-based solution, we come back to a level that is before 2018. Okay, and this third column represents the same budget, but taking into account the decarbonation that was proposed by the government to comply with the Paris Agreement. So you see that in each sector, the government is trying to make efforts. For example, the energy sector, the development of the solar panels is one of the factors that plays here in the reduction of the amount of CO2 that is emitted to the atmosphere. Same with the better refrigeration systems and improvement of the air conditioning. So we come back to a value of 828, and as early as 2030, we are very close to carbon neutrality. So a little bit of effort, carbon neutrality that should be achieved by 2015. Okay? So by including these natural-based solutions in the budget, taking into account the projection for decarbonization, we get closer to the national neutrality in terms of CO2 emission, which is a good news, and which should be something pushed forward to improve the protection of this aquatic ecosystems. Okay, so this is, just to conclude, a few of the activities that we conducted. We had workshops, technical workshops in the classrooms. We had field surveys. Stuart, you must be somewhere. I don't see you. I don't have my glasses. So this is the IBIS Island Conservation Society team in Beroche, posing for the pictures. And we had also activities involving the community with kids who came to learn about the seagrass and who learn about the terminology and the different names that we gave them. So this was a project led by Seagrass that Jim Mortimer was implementing more specifically. And among the 12 species, we reduced in 5 morphotypes. Okay, and those 5 morphotypes received a Creole name by asking the population, can be the fishermen who are used to that, or the kids at school who look at the different plants and say, okay, this looks like that, like that. And we came to 5 Creole names to describe those species. Okay? As I said before, the seagrass was named specifically, the generic term for all the plants that live in the lagoon is gaumont. Okay? And gaumont is seaweed, which is a plant that has an annual cycle that disappears at the end of the year and regrow. And or seagrass, which is a pluriannual plant. Okay? So the way of discriminating the seaweed from the seagrass and to recognize the different seagrasses based on their name was one of the main motivation of this project. And the Creole names were submitted to the National Dictionary, and now they are part of the dictionary, so they should be part of the vocabulary. And we've got posters in the lab, and each time we receive guests and we conduct these outreach activities with students or even the general public, then we introduce those Creole names that better speak to them than the Latin names that are commonly used. And together with that, so you see our names here and the plants, we had that displayed on buses, at least one bus, and it was a big achievement. And you see our colleague from CITAT is very happy to present this achievement. Some other activities that were conducted around the seagrass, because the NDC also aims at promoting research around blue carbon ecosystems. So the Monaco exploration and the Saya de Malala leg in October, November 2022 looked at a few of those habitats on the Saya de Malala in the Mascarenes region, and 13 Seychellois researchers were involved with Nuet. We've got two different site restoration projects. So we've got the Côte d'Or Prana, which is a recourse project that is sponsored by the Indian Ocean Commission that has just started now. So they had a meeting last week to initiate the implementation, and it will last for 3 years. And this aims at reducing the human pressure on the region of Côte d'Or to improve the resilience of those seagrasses without replanting anything, without making too much effort underwater, but just to try to find ways with the population to reduce the pressures in this ecosystem. And there's another one, a consultancy that ended in 2024 that should be happening right now for Baie-Sainte-Anne-Pralin. I think it's also a project that aims at expanding the marina on Baie-Sainte-Anne. And the problem of Baie-Sainte-Anne-Pralin is it's where we've got all these analogous species, Gaumont grandfeuille, that is very rare in the region and that we are happy to preserve. Yeah. Okay. And then finally, we had the Greenpeace expedition last April, where Murray and Stewart did some drives, did some drop cams as well, and took some calls. So this added to the initial data set about 166 drop cams, additional data that could be incorporated. And as I said at the beginning of this talk, the advantage of having had this mission was to refine the distribution on the rim of the Mahé Plateau. And this is all the different NGOs and partners that we had on this project. So this was the core team with the Island Conservation Society, the Future Little Trust, the German Aerospace Agency, the Ministry of Environment, and Oxford University. And these are all the partners, Save Our Seas, who hosted us for a couple of weeks to do the ground truthing around Sainte-Anne, around Davos and Saint-Joseph. The Seychelles Parks and Garden authorities who authorized us to go into the national parks to take samples. And also the dive companies that helped us by providing boats and dive equipment for us to ground truth very important regions and deep waters. Okay? And Wise Ocean, who helped us by providing some volunteers. That's all from me right now. I'm happy to answer any question if we've got time. So this is all the SDG goals that are ticked by the Seagrass conservation. Just to reflect. Yes, Murray.
Thanks, Jerome. You know, like the protection that Seychelles is committed to by 2025 is 50%,
yeah,
and 2030 and 100%.
Mm-hmm.
I guess my question is like, what is protection? Because when you show that map of the seagrass distribution of the marine spatial plant, almost everything fell within sort of zone 2 and
Zone 3.
Oh, it was the zone 3. Oh, okay.
We've got a bit in zone 2, and zone 2 is defined as medium biodiversity zone, and this medium biodiversity zone is very efficient at protecting species that happen in the water column. But the problem is that it does not exclude the utilization of substrate. It, for example, allows for sand extraction. And sand extraction is completely detrimental to the quality of the seagrass. So But there is hope because in this zone 2, we can have some activities that are under a permit, extraction permit, for example, where we can say eventually in policy that, yeah, if you want to extract there, here, because here we look at seagrass and there. Okay, so we can work on that. But there's a plan to have a blue carbon policy, but it takes time to put in place. There's been an inventory of the different instruments in the Seychelles legislation that would help make this conservation or this protection effort coherent. Now we need to fill the gap and see if there's room for a blue carbon policy. If yes, work on that. But apparently from our discussion with the SMS team, there is a better chance that we can reach this protection level by regulating more strictly the activities of some extraction in the region. So maybe there's no need to make a carbon policy, except if the government really wants to show that they have made progress in the applications. But for example, in zone 3, that's a little bit problematic. But fortunately, we don't have a lot of seagrass in zone 3. Most of the seagrass is present in zone 2.
Yeah, I guess that's not saying it's in zone 2, then typically it's in some
form of protection, but for seagrass, it's not a strong protection.
Yeah, sure.
It's kind of a light protection.
Yeah.
It's just a cosmetic.
Yes.
Yeah, when I was first in putting through the NDC in 2020 and 2021, that was sort of like that was my first protection it's great to say what we mean by protect. Farming as a environment, something we have to protect as well, but we can exploit stuff.
So here in terms of seagrass, the protection is strict. What is expected is that you don't touch the seagrass, you don't scrap out the plants, because if you scrap out the plants, the carbon that is contained in the sediment is remitted into the water. So the protection is not to take one quadrant and move it to another place. The protection is to keep that in place and not touch.
Which is interesting because if you look at disaster risk reduction management guides, their flood mitigation plan was to excavate the mangroves to make them deeper, and that is that. No, you remember that? On your way to the airport, they literally went in and dug out the channels to make them deeper so that they prevent flooding. I'm sorry, but that's what the president proposed for around the international school as well. And it was like, we shouldn't be planting that forest in.
Like also, there just, again, appears to be not a lot of communication. There's this beautiful pavement that's been built around the whole island, which is great, it's cool. In this section here, the school is just past the church. They're dredging out coastal vegetation, like in an area where already there's low sand and water currents, but they're dredging out the coastal vegetation so they can put this thinking in that is potentially awesome.
And I mean, there's integrated coastal zone management plan that was done that they have training on, but the departments don't look to one another. So I think that will work with most of those people as well. It's sorely lacking.
That's one of the reasons why we should not exclude a blue carbon policy at all, even if it's redundant with some of the policies, just to remind people that there are good practices and bad practices, and we need to make the case of those ecosystems.
If you go look at the Environmental Protection Act in Seychelles, key biodiversity areas, of which all seagrass beds around the island named, should be protected with no development. So that includes reef, hotel, all of that. But then the EIS can get passed through. So we've got our job cut out in terms of training people.
Ajit?
I have two technical questions.
Yes.
One is the data validation function. Data validation done by the machine or this machine has been
So it's a combination. So to train the algorithm, then we use data that we didn't use for the calculation. Just to train. So there are two types of machine learning. One is the algorithm that scans the satellite images, and the other one is the algorithm that looks at the satellite pixels and the photographs of the ground truth. Yeah. So from the top of my memory, we've got 73% of the receivers, which means that for one point where you've got seagrass, there is 73% of chance that it's seagrass. In general, okay? In some regions it's more performant because it's shallower. In other regions it's less performant because it's deeper, or the water color is more murky, and then you cannot. So basically, the ground truthing that we did was down to 25 meters, because for scuba operations it was the same. The deepest depth that could be reached in safety. Okay, so we limit our view of the seagrass in water down to 25 meters. But we know that they can go deeper, but we just did not account for that because we could not verify with the photograph that they were present. We know that they are present. We could not include that in the algorithm.
And also the related that you mentioned about machine learning, you use the classification technique.
So we use, so the Allen class was a tool that was developed in the 2010s, I guess. That was based on a community engagement where people could take pictures to describe the corals. And this Allen class shows a worldwide distribution of different categories, including sand, gravel, seagrass, seagrass and seaweed and coral. So we use the same algorithm as the Allen class, but we focus on the seagrass because the two categories, seaweeds and seagrass, were combined in the Allen class. So we use the same engine, but for the purpose of our project, we split it seaweed and seagrass to focus on the seagrass.
My question, nowadays they are using CNN networks. So why you use that CNN the classification? Because CNN can capture it more.
That really answers your question. I think that the quality of the sentinel imagery was not good enough to know network computing. Just the size of the types, 10 meters out of 10 meters, was not good enough to go to the deepest level. So we were obliged to do a statistical analysis and then to use the classification, which is statistics speed, rather than neural network and to small fine scales. But I'm not the specialist who work on satellite imagery, so I cannot really say why they chose this type of classification.
In any possibility, we can get access to those then we can compare the two results for the future.
But the problem is we don't have storage space.
Right.
That's the the
170 kilobytes of data in the workspace, and a few.
Maybe
they're on their server. I don't know where they're sitting. Where's the data sitting? Where's that one?
So on the Google storage space of the Google Science Engine. But I know that the German Aerospace Center has done exactly the same, has used Seychelles as a pilot study to do the same for all the region, from Mozambique to the north of South Africa, on the eastern African coastline, and Comoros, Mayotte, and the entire Madagascar region, including Mauritius. And so they have all the data that just need to be gone through. So the same algorithm was deployed now, but I heard that the company has now, the leaders of the company have made a speed of 1%, which is what happens when people become your homes. That's quite great. Good.
Also, one more quick question.
Yes.
Why does the carbon usage projection, why does refrigeration go so high?
Yeah, not only air conditioning, but we've got a huge storage facility in the harbor to host all the children. So it has just made a run.
But the amount of waste travel in the transport.
Okay, that's complex calculation because of so this the budget is positive for local.
Okay.
What's aided in the boundaries of our visa.
I'm asking.
Yeah, international flights and international cruise ships are not accounted for in the same way as the car, because they travel across boundaries. So that's the business of Andrew Jean-Louis, and who's a consultant for the Ministry of Climate Change and for the Department of Climate Change of NASA. And he's an expert on that. So if you're interested in knowing that, so all this is budgeted, but how it is accounted for in the national greenhouse gases budget for the purpose of the Paris Agreement depends on the guidelines that are provided by UNFCCC, which is the organism that collects all those data. They are specific methodologies for that. They have methodologies, and the problem is not all the methodologies for the different agreements that Seychelles is on converge. So for each agreement, there's a specific methodology to apply. So one of the things we need to converge against the methodology is that it avoids redoing the job all the time. But I had a look at the table that he provided. So the table has about 600 lines, and each line has CO2, methane, N2O, CFCs, and other greenhouse gases, and with a factor of conversion for CO2 equivalents, because not all of those greenhouse gases have the same greenhouse potential compared to CO2. So the table is massive, it's complex, and needs to be updated every year. So it's the job. It's very insane how this is to be calculated. So apparently the assessment is not made every year, so it's made every 5 years, and it's propagated from 1 year to another, just to make, just like the census of Seychelles. Only the census every year, but you've got data every year.
There is no any economic value of this carbon use.
So for the carbon, no. Oh, yeah.
Carbon credits. I don't think we're
So carbon credits means it's another process. So for carbon credits, you need to account for the carbon that is present and you need to increase it. So or increase the surface or increase the amount of carbon that is sequestered. For seagrass, it's very complex to account for. So that's for carbon, which would be the direct gain of that. But we've got all the other benefits, socioeconomic benefits for tourism, for example. Where you've got seagrass, you've got pure water, then tourists can enjoy swimming in pure water. It also removes some nutrients that, in the absence of a sewage system, we rely on the seagrass to avoid having red tides all the time because they take up some nutrients. So all these different ecosystem functions have benefits that can be translated into money. And the game is how to account for that. For example, in a region where there's an arena where they've got a lot of recreational fishing, with very rich people, everyone has to pay access to the park to go fishing, and then makes the economic value of this area extremely high because the price that people pay all over the year to have recreational activities in this space based on the ecosystem is extremely high. Regions like Sopin may be much lower, but if we consider that this feeds the population half of the year when we've got the southeast monsoon and the fishermen just go to their trucks, then we have to build a specific case for all the different regions we are interested in. We cannot apply an algorithm or a relationship based on the surface, because it depends on how the space is used by the population and what type of sectors play a role in this economy. So it's very complex. Like a hotel that would benefit from that, from the seagrass meadow. Now, if they remove the seagrass meadow, so they won't benefit from it. So how much do they count for activities that are not going towards conservation, but that are going towards destruction? How can we find those people for destructing? It needs to come with the value of the ecosystem. That's a very complex topic. We are trying to understand ways of doing that. I've made a calculation that I based on what was published in the intended NDC. Because in the intended NDC, the government of Seychelles said that if we want to remove this amount of emissions of CO2, we need to invest that amount of money, millions of dollars. So I took this into account in order to make an overall approach of economic approach of seagrass, and also for resilience, for coastal resilience. So we say we need to build walls, and we need that amount of money to build this number of meters of walls. So I took that into account and said, if the seagrass no longer account for the protection of the ecosystem of the land, then their value amounts divided by the surface, and that amounts to that. But it's not reflective of the true value of those ecosystems, because they provide much more services. So we need to map all the services that they provide by region, and we need to scale this up. But that's visible. Some people are doing that, and this is the only currency that we can demonstrate to the government, for some people to realize the ecological value to translate this ecological value into monetary value, because otherwise it doesn't do. Thank you very much. Was a little bit in the rush, but finally we did it.